So we're going to do the derivatives first of the inverse trig functions. We need to address the issue of finding the derivatives of inverses because you remember that logarithms are the inverses of exponentials and then vice versa. So we're going to talk a little bit about, why is this written all over? We're going to talk a little bit about now we're good to go. So we're going to talk a little bit about the relationship between the function and its derivatives inverse. So you can just kind of fold your arms and just kind of watch. This is stuff you've done before. We do this in pre-calculus. So a function and its inverse, let's just talk about this a little bit, and there's just there's a theorem that relates the slope of the tangent line for a function and its inverse, okay? And it's easy to get it confused because of what you learned in algebra and what you've learned about tangent and normal lines, but it's slightly different. And I'll help you to understand the difference here. So a function and its inverse. We have coordinates are reversed. Do you remember that? Like, think about the process for, if I hand you a function and I ask you to find the inverse function, what do? Switch the x and y and then solve for y. So the reason we do that is because I don't care what the function is, its inverse, even if it's a relation, its inverse is just the collection of points with the x's and y's reversed. That's it, across the board. So that's the relationship. So the coordinates are reversed. I think we know that already. But it's also true that the slopes of the tangent lines of the inverse functions are reciprocals of each other, not to be confused with opposite reciprocals. I'll give you a minute to write that down, but not now. Don't write it down yet. So here's why. If I have a function, here's my function right here. Here's my function. It's just a generic curvy function. It kind of looks like an x cubed function, but don't get caught up in trying to match a model to it. It's just a curving, continuous curving function. If I pick a point somewhere on the curve, I pick the point A, comma f of a right here, and I find, or I'm not finding because I don't know what the function is, but I'm estimating the slope of the tangent line here. I'm estimating the slope of the tangent line at that point to be about 2. Now, if I were to draw f inverse for this, f inverse, remember, is just a reflection over the line y equals x. So here's the line y equals x coming through here. If I reflect or flip that over the line y equals x, I get this curve right here. Okay. And the relationship between a function's derivative and its inverse's derivative is that it is not the opposite reciprocal, but just the reciprocal. You can see it here. If I find the derivative at f of a, by the way, right here I'm at about 2 point something, 3 point something, and so what I have to do is switch those two. So here I'm at 3 point something, 2 point something. Okay? So it's f inverse derivative is found at not the same point as f's derivative, but at the y comma x point. And so you have to switch those. So right here, the slope is 1/2. And you can see that they are definitely not opposite reciprocals, but they are always going to be reciprocals. So there will be times, and I'll give you examples of this later, but there will be times when you will not be able to explicitly find the derivative of f inverse. Like you'll be able to find f's derivative, but not f inverse's derivative. But what you can do is if you can find f's derivative, you can figure out f inverse derivative at y comma x. And you can go point by point and figure that out. So what you need to write down is the conclusion of this, is that the slopes of the tangent lines of the inverse functions are reciprocals of each other. So just write that down. That's actually a theorem in calculus. So just write that down. The slopes of the tangent lines of the inverse functions are reciprocals of each other. so we're going to use implicit differentiation to derive the inverse derivative of sine. Okay, we'll do that next. And then I'm going to give you a way to help you memorize the 6 inverse trig derivatives here, or just a way to group them. They don't at any point in the book put them all together. They kind of go through in a linear fashion. They derive one, like I'm going to do here, and then they derive the next one, and then the next one, and then they tell you how the other 3 are related to the previous 3, and it's just a string. It's like a continuous string. And I'm going to try to help you group these together in a way that will, I think, help you to memorize these. These are kind of harder to memorize. So I think just for homework tonight, I would just like you to just start memorizing. Because you could have these 6 memorized when you come in next time. Then after the quiz, we can practice using them in class with other people there to check you. Because, of course, we're not going to just be doing the inverse trig derivatives. It's like inverse trig with chain rule in it, product rule, quotient rule, all the other stuff. And so it makes it hard. So just see what I mean in a minute. Oh, this is just using that theorem. Let's do this first. So there's the fact we just wrote down. The slopes of the tangent lines of inverse functions are reciprocals of each other. So here's a function. It's pretty easy to find the derivative. It says find f of 1 here. So what's f of 1 here? I'll let you write down the function first. F of x equals x cubed minus 3x squared plus x minus 5. Let's find f of 1. So plug in 1, I get 1 minus 3 is negative 2, plus 1 is negative 1, minus 5 is negative 6. So I've got this coordinate 1 comma negative 6. And we're going to find f prime corresponding to that. So f prime of 1 is going to be whatever I get when I plug in 1 to the derivative here. So the derivative of this guy is equal to 3x squared minus 6x plus 1. So f prime of 1 would be 3 minus 6 is negative 3 plus 1, I get negative 2. So f prime of 1 is negative 2. So what that's saying is that at the point 1, negative 6, 1, negative 6, here we have this curve coming through here. I almost need my graphing calculator, but I don't think I can graph it just looking at it, but it's a cubic. And at 1, negative 6, it's coming down like this. And I don't know what all the branches do. We know it's positive. It might come back up again, something like that. That would be a negative 1, I think. No, that would be right. Something like that. So we might have something like that. It's a cubic. So right here at this point, the slope of the tangent line is negative 2. Does that look like it's negative? That's my sketch. So using this information, without ever finding f inverse, and by the way, could you find f inverse of this? Do you guys know how to do it? Okay, you know the process. Could you do it? No. You would switch the x and the y, right? So this would be y cubed minus 3y squared plus y. So you have, it's like having 3 different powers of y in there, right? Equals x, and then you have to solve that for y, so you can't solve it. But using this fact, could we find at least point-wise the derivative of f inverse at one point along the way? We can. We can find the derivative of f inverse. So f inverse. So f inverse prime at negative 6, we know. So remember, we can find f inverse at the y coordinate from f. Okay. So f inverse prime of negative 6 would be the reciprocal of this, or negative 1/2. And that's without ever finding the inverse of f. Okay. So, and you could, I mean, you could think about how you could program this in, but what this is saying is that even not knowing f inverse, like even though we can't find an explicit representation of f inverse, we could find f inverse prime at every y coordinate that we calculate f prime at. So if I can get f prime of 1 is negative, if I could find f prime of 2, which I could, whatever y coordinate goes with 2, I don't know what that is, but whatever y coordinate goes with 2, we could find f inverse prime of that y coordinate, and it would be the reciprocal. And so point by point, you can do it. You just can't do it explicitly. But once again, implicit differentiation comes in. Implicitly, we could play with it, but that's it. So write down this theorem, please. You could write down what's in blue here. It says if f is differentiable at every point of an interval I, so if f is differentiable, what does that mean, differentiable? You can take the picture, yeah. At every point of an interval I, so an interval I would mean like between 3 and 6, or between negative pi over 2 and pi over 2. So that's how we're going to use it here. But if f is differentiable at every point of an interval I, and the derivative of f with respect to x is never 0 on I, so that means on that interval that you've selected, as long as the derivative is never 0, then f has an inverse, and f inverse is differentiable at every point of the interval f of I. You're the freshman next door. Chasing each other around the room, that's what they perhaps. Based on the freshman I know, somebody took somebody else's pencil or something like that. Brawl. Not really a brawl. Yeah, I hear them laughing. Somebody's poked somebody else, or you know, taking a pencil. It went quiet, so yeah, somebody intervened. Okay, so if you kind of think back to pre-calculus, remember how we had to limit the domain to be able to make the derivative, or not the inverse into a function. Remember that? Remember the different x out zones, etc., etc. So we had to limit the domain so that the inverse would be a function. So consider the function y equals inverse sine of x. By this theorem above, we can say that because x equals sine of y is differentiable on this interval negative pi over 2 to pi over 2, and its derivative cosine of y is never 0, or is always it's actually always positive on that interval. Then y equals inverse sine of x is differentiable on negative 1, 1. Here's how I get the negative 1, 1. All I'm doing is plugging in negative pi over 2 here, right? Or just plug it into the original. Where's the here. So if you plug in sine of negative pi over 2 gives you negative 1. That's where the negative 1 comes from. You're plugging in right here. And then sine of pi over 2 gives you 1. You with me on the unit circle? So all that we're saying is that we're trying to establish that you can have a derivative for the inverse sine. But before we can establish that, we have to find a specific interval. It's the same as the domain of sine. Remember, their domain of inverse sine, I should say. Domain of inverse sine was between negative pi over 2 and pi over 2. So it was in this side. If I draw a picture, I think you'll remember this. It's between here and here, I don't know if you remember all that. Cosine, tangent's the same way. But the idea is that because on this interval, the derivative of sine is always positive. The derivative of sine is what? What's the derivative of sine? Cosine, okay. Would you agree that all the cosine coordinates here are positive? Remember, cosine is x's. So since the derivative of sine, which is cosine, is always positive, then the inverse derivative exists on what you get as outputs when you put in negative pi over 2 and pi over 2 as an input for sine. So from negative 1 to 1. So it's just telling you that, yes, the derivative exists, and here's how we go about getting it. We start with this, x equals sine of y. I don't think you'll need the stars. X equals, the stars are hints, star and the rectangle hints, but x equals sine of y. So, and you don't need to write this down, it's in your textbook, but follow through the implicit differentiation here. So x equals sine of y. What's the derivative of x? 1. What's the derivative of sine of y? Cosine of y, but why are they attaching this?
To get the derivative of y.
Okay, 2 words, chain rule. So, yes, you're right. So because of our understanding of implicit differentiation, derivative of sine is cosine of y, but then you have to attach a y prime or a dy dx. Okay, I'm using a y prime here to make it a little less writing. And then we solve for y prime, okay, just like you just did in the activity. So y prime is 1 over cosine of y. Well, here's the deal. Here's where the stars come in. It is. So implicit differentiation was the first thing. We got that. The second thing here is that we have an identity. We have an identity. Probably the most used identity in calculus from last year is this one. Cosine squared y plus sine squared y equals 1. If you solve this for cosine y, looks like this. Then you take the square root of each side, and we're only taking the positive square root. So we get 1 over square root of 1 minus sine squared y, and then sine of y, go back up here, it's just like what you just did in that activity. We replace sine of y with x. And then we have our explicit derivative in terms of x. So that is the derivative of inverse sine. It's a derivative of inverse sine. And they do, in the textbook, they go through a whole string of these. They do, they do inverse sine, and then they do inverse tangent, and then they do inverse, I believe, secant. They do those 3. Okay? And then they tell you the relationship between those 3 and their counterparts, I'll call them. Okay? So that's the derivative. I'm going to summarize all this in just a minute, so you don't need to write this down. Okay, I'm just showing you that the way we get inverse sine is a combination of that theorem in implicit differentiation, and then this is what you get. And this is how I grouped them. So this is what you needed for homework time. If you could just memorize these 6, then when you go to do your practice, which I'll have for you after the quiz on Thursday, you won't be looking these up the whole time. It would go better if you can do it. Because the derivative of sine is 1 over square root of 1 minus x squared. Okay? And I think you're going to need to write these down. They just don't present them, like in the textbook, they don't have them all together. So it's, I think, helpful to have them together. And the derivative of inverse cosine, look at this. Almost the same thing, but with a negative sign in front. That's it. And that's simply because of the phase shift between sine and cosine. There's a phase shift of pi over 2. So you can use what's called the cofunction identity to come up with or derive it. And you can read about it in the textbook if you like. But here's the derivative for inverse sine. Here's the derivative for inverse cosine. And they're kind of hard to memorize. If you could get these written down before you go in this fashion, it will really help. They are all in the textbook. But you see how I grouped them? The derivative of inverse tangent is 1 over 1 plus x squared. Inverse cotangent is just the opposite of that. And then inverse secant and inverse cosecant, you've got the same thing, just opposite signs. That's it. And yeah, these are rough ones to memorize. Only 4 more. We have 4 more to give you, and you have all of them. And we'll practice these on Thursday after the quiz.
Jason and Ryan Bond.
Right, so I'll give you examples of how these work. But I like to group them this way so that they have the derivatives that the textbooks will go through, and they'll derive them for you. We did inverse sine, but you can follow through the sequencing in the textbook for inverse tangent, inverse secant, and then just notice that their counterparts on the right there are all just the opposite signs of each of those. So that'll help you in memorizing these. What we're going to find is that x will not be x. X will be some other function in there, and so we'll end up using chain rule on these as well. So here we go. Here's some examples of what that would look like. So it says find y prime if y equals inverse sine of 5x. So notice that x is not x, it's 5x. So we're going to have to use a chain rule on this guy. Jot that one down. So we're going to find y prime if y equals inverse sine of 5x. So y prime is equal to, just using our new formula here, we've got 1 over the square root of 1 minus, place 5x in for x squared, just like that, times the derivative of the inside. So the derivative of the inside will be 5. And we could clean that up just a little bit. Y prime equals 5 over square root of 1 minus 25 x squared. The way I remember inverse sine's derivative and inverse cosine's derivative is they look like what you'd get if you were to solve the Pythagorean identity for one or the other. So if you solved like the Pythagorean identity for sine squared, you'd have sine squared of x equals 1 minus cosine squared of x. We saw that in the derivation of this. And then sine of x, at least the positive square root would be this, 1 minus cosine squared of x. And so, I mean, that's what we did to get the derivative in the first place, is we use implicit differentiation along with a Pythagorean identity substitution. So that's how I remember it. It's square root of 1 minus x squared, and then the inverse secant is absolute value of x times square root of, you're going to match that x squared minus 1. And so it's, instead of 1 minus x squared, it's x squared minus 1 under the radical for that guy. That's how I remember it. Example 3, it says find the velocity of a particle at t equals 16 seconds if s of t equals inverse tangent of root t. So s prime, velocity of t is equal to s prime of t, which is equal to, this is the derivative I like, it's 1 over, and it's 1 plus x squared plus 1, doesn't matter, just based on the commutative property. We have 1 plus x squared is the way it's written here. So we have 1 plus root t squared, but then we have times the derivative of the inside. So remember, t can be written as t to the 1/2. So the derivative of that is going to be 1/2 t to the negative 1/2. So there it is, using the chain rule. And if we clean this up just a bit, we've got 1 over, this is 1 plus square root of t squared is just t, it's 1 plus t. We've got this 2 down here that can move down in front of this. And then we've got this t to the negative 1/2, which is really just square root of t in the bottom. So if you want to clean it up, that's what it would look like. I might clean it up even more, but I could write it as 1 over 2 root t times 1 plus t. And then I'm going to just plug in 16 seconds. So v of 16 is going to be whatever I get when I plug in 16 where I see a t, 1 plus 16. So I have 1 over 2 times 4 is 8 times 17, 56, so it's be 136, 1 over 136. So we got 2 times 4 here, that's 8. 8 times 17 is we said 136. So 1 over 136. Whatever the units are. That's it. All right, example 4. This is find the equation of the line tangent to the graph of y equals inverse cotangent of x at x equals -1 on the interval between 0 and pi. So find the equation of the line to the graph. So we've got x equals 1. That's our x, x sub 1 is equal to -1. Let's go ahead and find our y sub 1, the specific y coordinate that goes with our x sub 1 there. So we've got inverse cotangent of -1. So it's asking what is the angle or arc whose cotangent is -1. So the arc whose cotangent is -1 would be, on 0 to pi, would be at, let's draw this value over here. So we are sweeping through 135 degrees, or in radians, it looks like 3 pi over 4. So y sub 1 is 3 pi over 4. So far what I have is y minus 3 pi over 4 equals m, and then x minus a -1, x plus 1. So we've got to find that slope. We find the slope by taking the derivative of inverse cotangent. Y prime is equal to -1 over 1 plus x squared. This one's just the straight formula because x is actually x. And then we're going to plug in -1. So y prime of -1 equals -1 over 1 plus squared, which is -1/2. So the equation of the tangent line to the graph of y equals inverse cotangent of x at x equals -1 on 0 to pi is this. We're going to pop in -1/2 for m, and there it is. All right. One more example here. This is involving inverse secant. So that's that third one down on the left here, the one with the absolute value in it. And so here we go. We have, this is find dy dx if y equals inverse secant of 5x to the 4th. So dy dx is equal to, we've got 1 over absolute value of 5x to the 4th. And the square root of this one, it's 5x to the 4th minus 1, and then times the derivative of the inside, which is going to be 20x to the 3rd. Okay, once again, the absolute value comes just from the derivation of the inverse derivative of secant. So you would go through the same process we did with sine implicitly, and as you go through that process, you'll end up with a plus or minus in there. And to get rid of the ambiguity with the plus or minus, you can slap that absolute value in there. That takes care of it. So what it ends up being is you have 2 different cases. One when x is greater than 1, one when x is less than -1, so in those outer ones with the domain. So here's our derivative. We could clean it up a little bit. Just place the 20x cubed in there. Be careful about simplifying these. If we're not positive what the domain of x is, then we can't lift off the absolute value, and therefore we cannot simplify it or cancel it with the stuff up on the top there. So unless you know what the domain of x is, there's a specific domain of x given. Be careful about that. Let's see here, we have 5x to the 4th. Oops, I forgot my squared in here. So make sure you get that. I'll put it in blue so you can see it. I left that out. The formula has absolute value of x or absolute value of u. I've just quoted it as absolute value of x times square root of x squared minus 1, and then noted that you need to use the chain rule where applicable. So we have to use the chain rule on this one because we've got a composition of functions right here. But that should be a squared in there. And so I could clean up this a little bit. It'd be 25 x to the 8th minus 1, and just leave it like that. Like I said, unless we know the domain of x, that it's positive, we can't lift off. Oh, actually, we could. We do know that. It's an even power here, so it doesn't matter. So because of this even power, what you'll find is with something like an even power, if you can establish that the domain of x is positive, that the absolute value will make no difference, you can drop that. So I have that question here. It says, can we drop the absolute value? Think about what happens to the expression if you plug in -2 or 2. So yeah, plug in -2 here, you get the same things if you plug in 2. So you could drop the absolute value, and therefore you could find it in a somewhat more simplified version here. It'd be like this. Okay. So just for the fact that I can drop the absolute value on this guy. And so we have 4 over x times square root of 25 x to the 8th minus 1. So, but when in doubt, just leave the absolute value in there and don't simplify. You don't need to worry about simplifying it. In this case, we can simplify it. So checking answers, things like that, you might find it in simplified form. And that's how they would simplify it, is establishing whether or not you can drop the absolute value, if it will make a difference. If you can drop it, then you can go ahead and cancel in this case. And so here we can. All right.